All right. Hello, everyone, and welcome to today's meetup. I'm Cato, and I'm a developer advocate at Viverica, home of Apache Flink. And today we are very excited to have Colin Germain here, who is the data science team lead at Vectra AI in Boston. Love Boston, it's great to see. And he's managing a team of data scientists to build advanced algorithms and machine learning models for cyber attack detection. He's also an avid open source developer and has contributed to Kara 2 ONNX and PyTorch to improve ONNX ecosystem. So he also has a PhD in physics from Cornell University and has been an active Python developer for over 14 years. He likes working across technical disciplines, from DevOps in the cloud to exploring new AI techniques, and then how to run those in production settings. So super excited for this topic today. All right, Colin, you want to take it off?
Awesome. Yeah, thanks, Kato. So I'm really excited to talk to you this morning, afternoon, or evening, depending on your time zone. I appreciate you guys all calling in. Today, I'm going to be talking about machine learning inference in Flink with ONNX. And before we get into the sort of strategy that we'll unpack in more detail, I want to start by sort of giving a motivating example for why real-time machine learning is so important. This is a toy example from the domain that we work in at Vectra, where I'm just going to sort of talk through this quickly, and it will really highlight why real-time is important and why machine learning is important. So in terms of trying to protect a network, there's a lot of things to do here, but just in this simple example, if you take these circles as computers, when one of these gets compromised, say by an adversary that has perhaps gotten a password off of a phishing attack, this is going to start really a chain of events, and we'll sort of walk through this toy model to see how it goes. And so an adversary is really going to want to be able to be permanent in this network, and so often the next thing that they'll do is set up a command and control channel. And that will allow them to be able to really have a permanent position in the network. And ultimately, what they're really looking for often is some sensitive data. And so further events will occur here, as you're seeing in the timeline, such as lateral movement, where they're traversing from the computer that they were in control of to where that sensitive data is. And ultimately, as you can see, this is sort of a great example for why real-time and streaming is really important. Because if you wait a day and tell the security professional who's helping to secure this network that something happened, you're going to miss the data exfiltration coming at the end here. And so in order to really protect these networks, real-time is really critical. The other part of this machine learning, so as you can imagine, there's a lot of different ways that external adversaries are trying to for example, do command and control. And so I won't go into the details about the cybersecurity in this talk, but ultimately, in order to really capture the variation of different types of techniques and exploits, being able to use machine learning is critical, because it's not really possible to write rules if then kind of statements in order to capture that. And so this example really goes to show why real-time and machine learning is critical. And why sort of being able to sort of connect the pieces, as we'll talk in this talk about Flink and ONNX, is really valuable. And the other part that I'll just mention before moving off of this is that scaling is also really important. So being able to take this example and scale it up 1,000 times is really key. And that's where something like distributed computing in Flink is really interesting. So with that, let's dive into the details of this talk, where we're going to be walking basically from a PyTorch machine learning example all the way into serving that in Flink. And so the really key sort of part of this chain here is the ONNX model that's in the middle here. And so what we're going to be able to do is have a machine learning model in PyTorch that we can then serialize into the ONNX binary format. And that is going to allow us then to serve it outside of Python, where we're going to be able to use Scala and Java in Flink, in the Flink framework, to be able to set up a streaming pipeline with it. And the other detail here is that we're going to be able to leverage the ONNX model in the jar, so it'll all be sort of packaged together, which is really quite nice for deployment purposes. And so I think one of the main points that I want to make in this talk is that by leveraging ONNX here, and we'll unpack what ONNX is in a bit more detail in the next couple of slides, but what we're able to do with ONNX is provide basically a contract of what the machine learning model is supposed to do. And that's really critical because it allows us to separate what is done in the model training phase of development from what is done in the production inference phase of development. So as you can imagine, often in companies, these can be totally different people who are working on the different sides of this ONNX model. And so you might have data scientists developing in PyTorch and Python, using a huge number of different Python tools to make it easy to iterate and develop. By being able to leverage ONNX in the middle here, we're separating that, and then we can essentially use whatever we want on the other side. And so in this case, we'll talk about Flink and being able to leverage that for the inference in production. And so that separation of concerns is a really powerful thing. And so this talk was actually motivated by another Flink, a Flink Forward talk in the past, where Py4j was used with ONNX and Scala. And I think, you know, the nice thing about this strategy that I'll talk about today is that you really get everything to sort of happen in the JVM more directly. Although, as we'll talk about, the model inference is done in C++, but ultimately sort of the packaging and deployment is a lot simpler from that point of view. So with this as sort of like the broad arc of what we're going to talk about in more detail, let's dive into ONNX a little bit more, because I haven't actually really explained what ONNX is and why it's sort of acting as this contract between the two sides that we showed. So ONNX is basically a model serialization format. It allows you to define a directed acyclic graph that basically defines the computation that you want to do. And so in this slide, I'm showing a very simple example. This is taken from Netron, which is an application that allows you to view these graphs very easily. I'll talk about that in a little bit here. But what you can see from this model that was trained using XGBoost, which is a gradient boosting approach, is that when you convert this to an ONNX model, you've basically got this input here, and then you've got a tree ensemble classifier as the operator here in this graph, and then you're outputting some set of probabilities. So this is a super simple example here, but it really sort of illustrates a few points. One is that you sort of can control the inputs and outputs pretty flexibly. In this case, the 0 times 6, that's actually 0 being a variable batch size in this case. So often you'll want to run your machine learning model over a variable batch depending on what sort of load you're looking at. And so the 6 is the actual feature size that's going into that classifier. But one of the other important things I want to mention here is that each operator in this graph is versioned, and basically that versioning allows you to really separate basically you're able to in the future still rely on the fact that because you knew what version the operator was, you can continue to serve it the same way anytime into the future. And what that means is that models are really backwards compatible, so that if you train a model and you get it into ONNX, you don't have to worry so much about whether the dependencies or libraries you use to train it are going to change, because the model itself contains all that information that's necessary to say, for example, this tree ensemble classifier, maybe it's version 13. And so if you look at the ONNX specification, you can say, okay, here are the arguments, inputs, and outputs, and you'll know exactly what is required in order to be able to serve that. And so the other part to mention here, and we'll dive into this in more details, is that the ONNX runtime, which is a library that Microsoft provides for running these in a very performant way, that again supports all these older versions of things as well. So if you have a model and you get it in there, you're going to be able to serve it in the future, which is a really nice perk. The other part that I'll mention, and I sort of touched on in the beginning, was language independence. So this model really has nothing to do with the language that you trained it in, nor the model or the language that you may serve it from. So being able to have that independence is really critical. It's effectively just a binary file that has these operators defined in it and inputs and outputs and some other metadata. Now, how do you actually get into ONNX with your model? Well, most ML frameworks have converters. We'll talk about PyTorch in this talk and some of the built-in features there. Other things like TensorFlow, Keras, scikit-learn also have converters that are dedicated to them, although some of those aren't necessarily in the package themselves. So it is actually at this point pretty easy to get your graph or computation into ONNX. There's been a lot of work in the open source community and also from Microsoft and other companies who have been involved with this. So it's for the most part pretty easy to do. I'll add one more thing on this in terms of pre-processing. So we'll circle back on this later in the talk, but you can actually define these graphs yourself. So you don't have to depend on the converters to do it. You can actually generate graphs more manually. And this can be really helpful if you're doing something like pre-processing, where often if you want to sort of put that into the graph as well, you may have to do some custom things. We'll come back to that in a little bit. I wanted to give sort of another example here of an interesting model. This is the MobileNet image model, and basically you can see that I more or less had to cut off the top many layers here because it's such a long model. But if you do open this up in Netron, which is that application that I've taken these screenshots from, you can actually click into each one of these operators and really dig into all the parameters. So for example, this convolutional layer here, you can click into that, see what the actual weights and biases are, and all sorts of information. So, anytime I'm working with ONNX, having Netron sort of on my side is really valuable because you can really diagnose and understand what's actually going into the graph. And so as an exercise, if people are sort of interested in getting familiar with ONNX, I would definitely suggest checking out the Model Zoo, which has MobileNet and some other pre-trained models that are pretty popular. You can download those, check them out with Netron, and click around and sort of get familiar with what this kind of thing looks like. And so these are the operators. As you can see, number of ones that may be familiar. I mean, simple ones like getting the shape so that you can do more sort of dynamic reshaping, as well as things like general matrix multiplication, which is effectively like a linear layer in a neural network. So these are some examples to get you familiar. Obviously, there's a deep neural network example here, and then more of a classical machine learning approach here. You won't see as much on the unsupervised side with ONNX, so that's one potential con. But overall, there's a lot of model support in the operator sets that are available right now. All right, so let's talk through an example of this sort of end-to-end. And I'm going to take a very simple example here, a pretty trivial model, and in this case, not even really using training at all. We'll come back to some more interesting machine learning pieces after we get through this, but I think it'll be easier to sort of talk through end-to-end what's going on by using this simple model. And so basically, I'm defining this class in PyTorch, which is a network. And what I'm doing here is I'm adding an offset to the constructor so that you can sort of hold that. And then the forward method here really defines what the computation should be in order to run the network. And in this case, we're doing, again, the most sort of trivial possible case here. We're just adding this offset to the input tensor that's coming in. And so, normally the real value, and as we'll talk about later, the value of this forward method is that PyTorch is going to automatically manage the backpropagation of gradients through this, so you can do training in a very easy and effective way. So I won't really dive into too much on that side now, but this is going to be sort of a very easy example to talk through the rest of the Flink pipeline as well. And so just to sort of show you what this does, if we define a network using this add offset class, and we give it, say, the example 5, then taking a tensor and passing it through the network is going to offset it by 5. So pretty simple. And we're going to then take a look at how this model progresses through the rest of the pipeline that I showed before. So what does this look like getting into ONNX, right? So as I mentioned, PyTorch actually has very nice support for exporting to ONNX directly in the library. There's a couple of things to keep in mind when you're doing this. So you're going to provide the network that was trained. You're going to also provide some inputs. And because PyTorch is pretty flexible, you can see that I was basically writing Python code to write the layers. Basically, it uses some level of tracing to deal with dynamic types of models. So if you're dealing with a dynamic model that has some more advanced logic in it, that maybe isn't sort of a straight sequence of layers, as we'll talk about a little bit later, you want to be a little bit careful here what sort of inputs you provide, because that can affect what the actual graph that gets generated from that is. And so, you provide sort of a file name for this. Again, this is going to go into a binary file, input names and output names. This just allows you to sort of reference that when we're putting the inputs in. And then the last thing, which I think is really important, is getting these dynamic axes. This allows you to do stuff like batches. So if you have, for example, wanting to be able to provide any size batch to your model, in this case, that's what we're doing here. We're saying that the 0th, basically index of the tensor is going to be of batch size, and then that sort of being mapped to the end output. We'll see this a bit more in future examples. And so not only is it important for batch sizing, but often if you're doing, say, time series or variable length sequences, getting all these dimensions right is an important thing to think about. So with that, we've got our ONNX model. You can see, again, it's pretty trivial. We've got some input coming in. It's of a particular batch size, and then it's going through the add operator with the number 5 here and giving us the output. So how does this look in Scala in setting ourselves up for running this in Flink? So we're going to leverage onnxruntime, which, as I mentioned before, is basically a C++ library developed by Microsoft that's out on GitHub that you can check out and leverage. They publish basically some Java packages for that. So there's a Java API that we can leverage in Scala. And so we're going to use basically this onnxruntime environment and onnxruntime session from this onnxruntime package. And we'll talk through sort of how this is leveraged as we go. So I'm going to create basically a class to hold a model. So for a given model like the one we just showed, we're going to have a class that basically holds on to that. And given the resource name, as we'll see in a second, we're going to be able to load that model up in memory and be able to use it to do inference. And so we're going to pass in the environment. This is more or less sort of a handle on basically the ONNX environment generally, whereas the session here is really the graph itself in memory as a representation and what you're going to use to do the inference. So for each model that you might want to serve, if you wanted to serve many, you would need an individual session per model, unless you were to do something more complex like putting them in the same graph. All right, so with that object, what we're going to do is provide a load a load method here that basically grabs the ONNX model from the jar. And so this is one sort of nice piece here where by grabbing it in this way as a byte array, we can basically leverage the fact that if we package it with the jar, it'll be available to the code directly when we run it in Flink. And so that's nice because you don't have to worry about sort of connecting to some other endpoint or pulling down a file from some other place. It's all effectively bundled together. And so as you can see here, what we're doing is basically taking that byte array, passing it into create session, which gives us our session for ONNX runtime. All right, so at this point, we have an object that can handle these models, it can load it up and keep the session going. And so what we want to turn to next is actually leveraging Flink more and leveraging the rich map function in order to hold on to this model and be able to use it for inference. And so, following on our example, I'm going to create basically this add5 class, which extends rich map function, basically mapping between a floating point number and another floating point number. Now, in your model, you're probably going to want to use other types and maybe expand the features that are coming through. So there's a lot of room here to change things up and modify in order to fit what you're actually trying to predict and what your outputs are actually going to look like, because you may have multiple outputs, for example. So in this case, we're holding on to one of these ONNX runtime model classes that we just talked about. And the nice thing about the rich map function is it allows you to sort of load and close when you're done this model. So we're able to sort of like cleanly manage the session for the model pretty easily. You can see here, I'm just basically grabbing this ONNX file using the runtime model that we mentioned. And at the end here, when we shut down, we're going to close the session in environment. All right, so that's sort of the bookkeeping side of things. But the more interesting part is this function, which is really doing the inference, and we'll sort of talk through it line by line here. So starting off, what we're doing is we're mapping, right, as we said, between these two floating points. Again, if you were doing something different, you would modify these types quite a lot and just change what sort of inputs are coming through. But ultimately, what we want to do is get these into an ONNX tensor, which is what holds the data and basically passes it off into what's accessible then to ONNX runtime, which as a C++ library isn't necessarily in the JVM directly, right? So we need to be able to sort of pass this off. And in this case, what I'm doing is basically telling it the environment that we're putting it in, and I'm just putting it in an array because as we define that model as a variable batch size, we need to give it an actual array in order to meet that type. And so next, we're basically defining all the different inputs. In this model, right, there's only one input X. So we can map that to a tensor that we just created. And there's a little bit of getting to Java here from Scala, but pretty straightforward for the most part in order to get our inputs, which are actually going to be run through the Java API of ONNX runtime. So that's sort of setting up the tensor and inputs and everything. Next, we can really start running this through the model. So being able to use model session run, this is really the sort of main inference piece here, where we're passing in the inputs and able to get our results. And so there's a bit of indexing and sort of typecasting to get the results out. In this case, again, we have sort of an array coming back because we requested that it was a variable batch size. And so we need to grab sort of the one float. We know already that we're only passing one in, so we know we'll get one out in this case. But as you can see, if you're developing a different type of model, the main pieces are here. There's not too much more that you need to do outside of thinking about how you might want to deal with multiple outputs or things like that. So this is really sort of the meat of making the prediction. So now that we've seen that, let's talk a little bit more about just some of the packaging pieces. So as I mentioned, as long as you put the ONNX models in this source main resources directory, those will be accessible to the onnxruntime class that we showed. And we can verify that these files are in there in the jar after we've built this. So just looking to see, this ONNX file. And then the other thing I just wanted to point out is that the onnxruntime libraries are involved as well. So you basically have everything you need in order to pass this off to a Flink cluster and run it as a job. So with that, I'm going to just sort of give you a view of what the demo looks like here and give a very simple example again for this. So, if we define basically an array of numbers here, we can stream through these, making sure we get those to float before we pass it to our add5 rich map function, and then we can print those out. So if you do run this on a cluster and pass the jar, this is what you would expect, and no surprises, right? We got our offset here, and so this is just more or less showing the full end-to-end view of this. Obviously, the machine learning part is not very exciting in this case, and so let's talk a little bit more about other machine learning pieces. And this one, MNIST, I'm sure you probably heard of this. It's a very it's sort of the classic problem that people solve as an intro to things like PyTorch or TensorFlow. So if you look out for tutorials, this is what you'll see. And just to sort of unpack it for those who aren't familiar, basically the task is to classify a digit that's handwritten from a 28 by 28 pixel array. And so here I'm just showing what this model looks like in PyTorch. So again, very similar and actually not that much more code than what we showed before. Here we're using a sequence of different layers, having 2 linear layers with activation function in the middle here and a softmax at the end. And what you can see is that I'm also adding sort of a flatten here to just make it so that it's one long array during these. And so, the value of using PyTorch really comes as we're now leveraging more neural network approaches, because we don't have to worry about the backpropagation calculations. Those are going to be handled automatically just by the fact that we defined our forward function here. And so the code to convert this into an ONNX graph is effectively the same as what we showed before. There's really not much else to it. You can actually see that we're using the same batch sizing approach here in order to make that variable so that we can just decide what we want when we're running it in terms of how many batches we might put in. And as you can see, the graph itself, as we saw earlier, has these general matrix multiplication operators, and all the ones that you would expect here, coming down to the batch size by the number of classes that we're predicting here, right? So we're going to get the probabilities of it being a particular digit coming out of this. So this is a simple example. For all the code that I've shown so far, I'm going to show a link to GitHub where you can check this out, try it yourself, and I would definitely recommend that. After the talk, I want to talk about one more sort of interesting machine learning example. And so if you've been paying attention to the NLP world recently, there's been a lot of interesting things coming out in terms of transformers, which are sequence-based models that work really, really well. And so I want to talk through a little bit this example, which is a basically optimized smaller version of BERT, which is a transformer model out of Google research, and sort of how you can get that into Flink as well. And this is an interesting model because it's already been trained. It's been trained on a vocabulary of words, and these transformer models in NLP are generally used for things like predicting sentiment, doing translation, other types of word tasks that they really excel at. And so given a pre-trained model, you can take that to a transfer learning step where you actually basically continue to train and modify some of the layers or add new layers in order to do a new type of prediction task. And so there's a lot of great resources out there that enable you to do this quite easily in order to get to an ONNX graph that then you could use through the same process that we showed here. And so this is an example of the Hugging Face Transformers library, which is a Python library that allows you to really grab these pre-trained models and do transfer learning pretty easily. Here I'm showing basically being able to import the BERT tokenizer and sequence classification models for this, and then reaching out and grabbing this BERT Tiny, which is a smaller version of the transformer model. These can tend to be quite big, as you can imagine. And so I just wanted to highlight this because there's a lot of cool things on the Python side where it's easy to get an existing pre-trained model, do this transfer learning, and really approach a problem that would be very difficult otherwise, and may not be as accessible in Scala if you wanted to do production there, right? And so let me show sort of what this looks like on the conversion side. So once you've done your transfer learning and training, it's very easy using the Hugging Face Transformers library to get this out into an ONNX graph. And so as you can see, it only takes a few lines of code to generate a graph here. They include some really nice features as well in terms of optimization of the graph and quantization as well. So if you're trying to eke out performance and think about the best way to serve these models, that can really go a long way. The one thing that I will note, and one of the reasons I'm not sort of showing this off more in this talk, is that the tokenizers here are still not really part of the graph. And so that's something that if I get some sort of open source time to work on, I'll probably try to get into this library. But you'll notice a lot of open source libraries still don't have this pre-processing available necessarily, so that you may be able to get the graph out into ONNX, but the pre-processing stages tend not to necessarily be going in, and there's sort of an expectation of them being in Python. So that's one thing just to keep in mind as a caveat here. And so just to sort of see, again, I had to clip this graph to make it visible here for the slides. But it's showing here some interesting pieces like multiple inputs. There's an attention mask in this case. This is a sequence-based model. And you can see, just a number of pieces starting to actually get into the attention here, and matrix multiplication as it gets further down. So I won't talk about this model too much more in detail, but I think it's an interesting, motivating example of how easy it is to leverage Python to develop these models and create these graphs. And there's still a few rough edges in terms of pre-processing and other pieces, but it's actually pretty accessible. And you can then leverage the method we talked about to be able to serve that in Flink. So just to sort of recap and talk through some of the pros and cons here. So from what I've described, I think one of the great pros is that being able to do this inline in Scala Flink allows you to leverage the sort of full capabilities of the Scala language in Flink and the framework that's available there. So there's a lot that you can then do directly in Scala. And as we talked about, being able to separate the training dependencies and all the sort of Python world from the production inference is actually very valuable. That having that sort of contract in the middle can decouple those two pieces very effectively, which is great. And so the other piece we touched on, being able to package this in the jar and just have it available, is really nice from a deployment perspective. And then obviously in terms of Flink itself, being able to do partitioning, grouping, and really getting all the things you need in order to create the feature vectors and sort of inputs that you're going to want to pass into the model. That's where I think this method is really interesting, because you can leverage all of what Flink is able to do there. In terms of cons, the couple of them, and I think some of these are more pain points and things that are solvable, but with more extra effort. In terms of the model size, we are sort of pulling that out in bytes, and we're basically putting that into memory in order to serve it. So there is some memory being taken up. If you have a 500 megabyte model, like some of the transformer models, that can become a problem. So thinking about that and being careful with it is important. This goes also for batching considerations. So making sure that you're sort of leveraging the model as effectively as you can is something that takes a little bit of tweaking and tuning to think about, and performance testing. This also goes towards hardware acceleration. So often deep learning models really need GPUs in order to get inference times that are going to be appropriate for your use case. And so what I showed today is using the CPU backend of ONNX runtime. There is a GPU backend as well, and there's a few other backends available through ONNX runtime. So while this isn't necessarily a problem, it requires some extra effort beyond what we showed today in order to get this. And I just want to call out the external resource framework here, which can enable you to sort of leverage GPUs with your TaskManager as a way of doing this. And the last piece that I mentioned earlier, pre-processing, it's definitely possible to do, and you can really create your own custom ONNX graphs, which can then be sort of melded onto other graphs that you may have converted from PyTorch, for example. But the challenge here is that that can take a fair amount of extra work. It's not sort of plug and play as easy as what you saw earlier. And so that takes a bit of consideration as well. So with that, I'll conclude. As I showed, ONNX really enables this real-time machine learning in Flink, and it nicely separates the Python training code from the Scala production code. So that can be a huge win, especially for data scientists who want to be able to iterate with lots of different packages and not be tied down to the inference, production runtimes. And so, here's a link to the GitHub page where you can get the source code that we talked about and sort of walk through the models yourself. You can run it on a local Flink cluster. There's instructions for doing that. And so hopefully this is interesting to play around with. And with that, just sort of a final shameless plug here. We are hiring at Vectra, so if you're interested, please reach out. We'd be happy to chat on that as well. So with that, that was all I had today, and I'm happy to take any questions.
Colin, thank you so much. That was really, really fantastic. And we've got a couple questions in the chat here. So the first one, you answered a little bit. They asked this earlier in the chat, but I'd love to hear if you have more to say on it. So this is, how does Flink work with TensorFlow-based models, especially for large NLP models based on transformers like BERT? And then also, is it based on TensorFlow?
Yeah, so that's a great question. So TensorFlow and ONNX are separate, and there's actually a package called TensorFlow to ONNX, and if you're using Keras, it's Keras to ONNX. That will allow you to convert your TensorFlow model into the ONNX graph. And so once you finish training, basically, or if you have a checkpoint or something, you can convert that over into the ONNX graph and then serve it using ONNX runtime. And yeah, definitely in terms of large models, hundreds of megabytes, there's a fair amount of tuning and tweaking that you have to start thinking about. This comes back to some of the hardware acceleration pieces that I mentioned as well, wanting to be able to use GPUs or other resources in your TaskManager. And so I think, yeah, all those sort of come to play when you're trying to get these bigger models to run in an appropriate time.
Awesome, cool. And then, and thank you for that one. So our next one is, why did you use ONNX instead of Java API, PyTorch, or TensorFlow?
Yeah, so I think the real benefit of using ONNX is it's not tied to any specific platform, right? So if a data scientist wants to write something in PyTorch, they might turn around and want to use a feature in TensorFlow the next day. And if you're tied to one of these libraries, then you don't have the flexibility to do that, and you're really sort of stuck saying, okay, well, we need to support PyTorch explicitly. Whereas with ONNX, it's like, well, here's how the actual model should play out. This is the definition of the model. This is the sort of schema for the graph. And it's really language agnostic, framework agnostic. And one point I'll add there, if you are using PyTorch and you wanted to switch to TensorFlow, you can actually use ONNX as sort of a vehicle to go between the framework. So there's actually some really interesting properties with just being able to define something that's agnostic to the actual training library that you use.
That's awesome. I love that point. Cool. So then, we've got a couple more coming in. So have you experimented with TensorFlow models with TensorFlow Scala project?
With TensorFlow Scala project? No, so I can't really comment on that.
That's totally fair. Yeah. And then, we just have comments for the rest of this. So because of training models in Python. Yep. I'm going to give it another just couple seconds here. Everyone who's listening on YouTube, please feel free to add in any other questions that you might have on the chat there. Looks like someone might be typing, so I'll wait one moment there. And while we're waiting on that, I just want to thank you again so much, Colin. This really was really great. It looks like they stopped typing. So I think that's it for our questions. If people have extra questions, do you have a way that you'd prefer for people to reach out to you, or just check ONNX online, or?
Yeah, no, that's a great question. So, I mean, anything specific to the repo itself, if you have, questions, feel free to create an issue on GitHub and we can chat about it there. Feel free to reach out to me on LinkedIn, especially vis-a-vis the hiring. And so, definitely feel free to reach out on both of those areas.
Great, awesome. And we've got a couple people thanking you as well. So, and again, thank you so much. And I hope you have a great rest of your day. And thank you everyone who tuned in today.
Awesome, thank you.
Cool. Cheers.
Bye.